Okay, we are looking at types of relationships. So like we said in the last video, we were only looking at linear. Now we're going to look at linear or exponential. The big difference is that exponential is going to create a curve, whereas linear was more of a straight line. So we're going to look at these examples down here. We can kind of tell how this graph tends to curve. The other graphs, if we had to group them together, are more of a line. Okay, so we're going to talk about linear versus exponential. We're going to talk about strong versus weak, positive versus negative, those kind of things. So first off, which ones show a strong relationship? So strong means that they're going to be close to the line. So let me draw this actually through this shape here instead of on top of it like that. So strong would mean I have a good amount of the points and they're close together. So I would say strong is going to be B and D. A and C are both pretty spread out. Which ones show weak relationship are going to be A and C. Linear is going to be A, B, and D. Which scatter plot shows exponential? So we're going to go with C for that one. Which one shows a positive relationship? Mean we're increasing from left to right. I could say A or D. And then which scatter plots show a negative relationship going down from left to right are going to be B and C. Now, I could see where maybe you could make the argument that D might look slightly curved because of this little curve right here. So this one is actually kind of tricky. I'm not 100% sure because I think you could make an argument for D going either way, being exponential or linear. I think you would need to actually run the models to determine what that one is. So I could see that maybe D is exponential. So maybe it goes exponential instead of linear. It's kind of tricky on that one. I'm not 100% sure what they want us to do with that one. Okay, number 2, it says the scatter plot we have here shown represents the games released on Steam since 2003. Interpret the variables in the context of the question. So interpret the variables means just say what's explanatory, which is X, and what's response, which is Y. So X is going to be our years since 2003. Response is number of games released. Okay, describe the relationship between the years 2003 and the number of games released on Steam. So I want to say, when it says describe, I want to say things like positive, negative, strong, weak, linear, exponential, those kind of things. So we can tell that this shape is curved. So we're going to say this is exponential. We can tell it's going up from left to right, so it's going to be positive. And we can tell that the dots are pretty close to the line, so we're going to say that that's strong. Okay, so those are 3 words I could use to describe that. Example 3 says, in the early 2000s, the exponential equation, they give us this equation, could have been used to model the population of the world, where Y represents the population in billions of people, and X represents the years since 1900. Based on the given equation, estimate the population in the year 2020. So this is where we're starting from. This is the year we have. So since it's the years since 1900, I have to figure out what my X value is first. So I'm going to have to subtract. So my X value is going to be 120. I don't want to plug 2020 into this problem. I want to plug 120 in. So I'm going to go 1.6, and then we're going to fill in everything we have, and we're plugging in 120. Now this is where we have to remember our order of operations. We always have to do our exponents first. So in our calculators, we got 1.0134. Our exponent button is here. 120 equals, and then this 1.6 is next to it. Remember, when something is next to it, it means we multiply. So times 1.6. We've got 7.9037. Okay, so depending on what you want to round to, which this doesn't tell us what to round to, let's say it's approximately 7.9 billion, because it said it was in billions, people. Okay, is this model still representative of the population today? So the population today, I don't know what it is, but I looked it up and it says it's about 8 billion. So this is a good model. I'm just going based off what somebody told me. So I think it's a pretty good model. It's close. Example 4. The table below shows a recent graduate's credit card balance after each month of graduation. And then we have an equation, a best fit here. Based on the given equation, estimate the amount of credit card debt 1 year after graduation. So we have to remember that 1 year is 12 months because this specifically says each month after graduation. Okay, this chart only goes up to 8 months, so 12 would be out here somewhere. So this is definitely going to be extrapolation because we're outside of the set of data. So we need to take the information we have and we're plugging in a 12 for 12 months. So 1.196, use our exponent button, 12, hit equals, and then times 522.89. So we've got 4,479.04. Okay, I rounded to 2 decimal places because it's money. Okay, so since this is money, I rounded 2 decimal places. Does the y-intercept make sense with the context of the question? So if you guys remember, the a value in exponential was our y-intercept. Okay, so our y-intercept is going to be 0.522.89. This is our coordinate. If you couldn't remember that, you can always plug in 0 to get a y-intercept to the equation, and you could have figured it out that way. Okay, so in this case, this is months, and this is money. So at month 0, the predicted debt is okay, so they're saying right at graduation, because that's month 0, the predicted debt is $522.89. I hope we're not graduating. I hope this is college graduation, not high school graduation. Okay, so now you have day 5 practice, which is similar to what we've talked about, where you're talking about y-intercept, you're talking about plugging in values, so similar to what we already did.